Hello everyone, Zach here. Today I'm analyzing a potentially volatile severe weather setup unfolding across portions of the Ohio Valley and Central Appalachians, valid for today, Monday, April 14th, 2025. If you're in West Virginia, southeastern Ohio, southwestern Pennsylvania, or adjacent areas, this is your time to stay weather aware. Let's walk through the latest data and what it means for your safety. Now, let me explain the broader setup driving today's risk. A cold front is sweeping southeast across the Ohio Valley today, linked to a storm system over the Great Lakes. As this front moves in, warm, moist air from the south is being pulled northward into places like Kentucky, Ohio, West Virginia, Pennsylvania, and Virginia. Thanks to breaks in the cloud cover, we'll see temperatures climb into the 70s by this afternoon. Dew points in the mid to upper 50s will combine with the warming surface to create just enough fuel for storms, what we call mixed layer CAPE, with values ranging from 1,000 to 1,500 joules per kilogram, which is moderate instability. And importantly, there's very little convective inhibition, meaning the atmosphere will be ready to pop as soon as the front provides lift. We expect scattered thunderstorms to form by mid-afternoon, beginning in northern Kentucky and southern Ohio, then pushing eastward into West Virginia, Pennsylvania, and Virginia through the evening. Some storms will remain isolated, but others will grow into clusters or bowing lines capable of producing large hail up to 1 to 2 inches in diameter, damaging winds in excess of 60 to 75 miles per hour, and a few tornadoes, especially where local moistening enhances low-level rotation. Let's take a closer look at southwestern Pennsylvania and areas of West Virginia, including key areas like Pittsburgh, Latrobe, Indiana, Clarion, Wheeling, and Weirton. This region has been placed under a marginal risk level 1 out of 5 for severe weather, which is the lowest tier on the Storm Prediction Center scale, but that does not mean that you should dismiss the threat altogether. So what's driving this setup? Well, north of the warm front, we'll likely see elevated convection, meaning storms that form above a cooler surface layer. These storms tend to be less intense, often producing lightning, brief downpours, and perhaps small hail. However, south of Interstate 70, there's more potential for surface-based storms, especially if the clouds break up and temperatures rise into the mid-70s with dew points approaching the upper 50s. In this narrow zone of better surface instability, scattered thunderstorms may develop late this afternoon into the early evening hours. If they do, they'll tap into enhanced low-level shear and modest CAPE, making them capable of producing strong wind gusts, potentially in the 40 to 60 mile per hour range, small to marginally severe hail, and a very isolated brief tornado if storms can remain rooted near the surface and interact with any lingering boundaries. Additionally, there's some concern for storm interactions with terrain-enhanced flow, especially in areas south and southeast of Pittsburgh. That could locally boost low-level helicity and help organize convection just enough to cause concern, particularly in Greene, Fayette, and Westmoreland counties, which are closer to the better moisture plume. While this isn't a high-end severe weather day for southwestern Pennsylvania and portions of West Virginia and southeastern Ohio, the setup still warrants close monitoring, especially for folks commuting during the late afternoon rush or planning evening activities. All it takes is one well-placed storm to cause issues. Let's break down a critical update from the Storm Prediction Center regarding the severe weather potential for central and southern West Virginia today, April 14, 2025. We began the day with much of the area, including Charleston, Beckley, Elkins, Clarksburg, Snowshoe, and Sutton under a slight risk or level 2 out of 5 on the SPC scale. That meant scattered severe storms were expected, with hazards including damaging winds, isolated large hail, and conditional tornado threat, particularly if surface heating and low-level moisture aligned ahead of the approaching cold front. However, by late morning, the SPC issued an upgrade, elevating a large portion of this region into the enhanced risk, which is the level 3 out of 5. So what changed? This kind of midday escalation usually points to a more volatile atmospheric setup than originally anticipated. And that's exactly what happened here. Improved model agreement, which means that high-resolution guidance, including the HRRR, the ARW, and the NAM 3 km, showed more aggressive destabilization across West Virginia, especially in valleys and lower elevations where cloud breaks enhance solar heating. We also have a forecast of higher instability in the mixed layer CAPE values. They rose into the 1,500 to 1,800 joule per kilogram range, and capping was weaker than expected. This will allow deep convection to initiate more easily, especially by mid to late afternoon. We're also seeing stronger wind shear, with the bulk shear values of over 45 to 50 knots combined with elongated hodographs which supports storm organization. This means the environment is favorable for supercells, bowing segments, and storm clusters that can quickly rotate or surge forward with damaging outflow winds. We also see a storm mode shift. Earlier in the event, there's now a higher chance for a discrete supercell or two capable of producing large hail between 1 and 2 inches in diameter, isolated tornadoes, particularly along and east of the I-79 corridor. As the event progresses, storms are expected to congeal into bowing segments, which could bring damaging straight-line winds up to 75 miles per hour. Storm initiation is expected between 4 and 5 p.m. beginning across southeastern Ohio and eastern Kentucky. These storms will move into West Virginia between 5:30 and 7:30 p.m., affecting cities like Charleston, Clarksburg, Elkins, and Snowshoe. The peak severe weather threat will occur between 6 p.m. and 10 p.m., with the risk tapering off late tonight as instability disperses. If you're located in Charleston, Elkins, Beckley, Sutton, or Snowshoe, or anywhere within the orange enhanced risk zone, you now face a heightened threat for severe weather impacts. This is no longer a low-end event. The combination of instability, wind shear, and mesoscale boundaries creates a favorable setup for damaging storms capable of significant impacts over a wide area. This enhanced risk upgrade reflects a maturing weather system that has evolved more aggressively than early forecasts suggested. When the SPC makes a midday adjustment like this, it means confidence is growing in not just the coverage, but the intensity of storms to come. Take this seriously, folks. Charge your phones, review your severe weather safety plans, and make sure you have multiple ways to receive warnings, especially if you're in a region with limited cell service or mountainous terrain. These storms could develop quickly and turn severe with little warning. As we shift north into the Pittsburgh forecast area, we notice that much of southwestern Pennsylvania, including Pittsburgh, Wheeling, Butler, and surrounding towns, sits well north of the northern fringe of the SPC's 2% tornado probability contour for today. Now, on paper, 2% might seem insignificant, but it's important to understand what that actually means. This indicates that there is a 1 in 50 chance of a tornado occurring within 25 miles of any given point inside that shaded area. It's a low-end risk, but it's still very real, especially considering how quickly localized conditions can change. Let's talk about the setup. In this region, we're expecting limited surface-based instability, meaning the air near the ground may not be quite buoyant enough to strongly support deep convection. Temperatures will likely peak into the low to mid-60s, and dew points will hover near the 50s, just enough fuel for modest updrafts if sunshine breaks through and erosion of the cap occurs. But what makes this setup worth watching is the strong low-level shear and helicity, or in simpler terms, the twisting of winds with height. This shear is being driven by a strengthening low-level jet, which enhances storm relative helicity values across this area, and that can compensate for the lack of instability in certain situations. So here's the takeaway, folks. If a few discrete storms manage to develop ahead of the main cold front, particularly in areas south of I-70 where surface conditions are slightly more favorable, these storms could briefly become supercellular and produce a tornado, especially if they interact with the mesoscale boundaries or localized terrain effects near the Allegheny Plateau. Also, keep in mind that these types of setups can sometimes result in quick spin-up tornadoes that occur with little warning, particularly embedded within clusters or bowing segments. Now, let's talk about the SPC tornado outlook centered over the Charleston, West Virginia forecast area where things are looking more concerning. A large swath of the region stretching from Huntington to Charleston, Parkersburg, Clarksburg, Elkins, Sutton, Snowshoe, and even areas near the Virginia-West Virginia state line is under a 5% tornado probability contour. Now, that number might not sound high at first glance, but here's the reality of it. A 5% risk means that there is a 1 in 20 chance that a tornado will occur within 25 miles of any point in that zone. In meteorological terms, that's a notable and actionable level of risk, especially given the region's complex terrain, which can obscure tornado visibility and make warning dissemination more difficult. Let's talk about why this is happening. As a cold front pushes east-southeastward into the Ohio Valley, it will encounter an environment rich in modest to moderate instability with mixed layer CAPE values nearing the 1,000 to 1,500 joules per kilogram. We'll also encounter strong, low, and mid-level wind shear exceeding 40 to 50 knots. We also have sufficient moisture return with dew points in the upper 50s to near 60 degrees Fahrenheit. and terrain-induced mesoscale boundaries, which can further enhance localized shear. Model guidance, including high-resolution runs of the HRRR and the ARW, show a trend toward broken supercells initially developing ahead of the front, followed by upscale growth into line segments or QLCS-type squall lines. These squall lines can feature embedded mesovortices, which are small-scale circulations capable of quick spin-up tornadoes, and they're often difficult to detect and short-lived, but still very dangerous. Timing-wise, we expect convection to initiate between 3 and 5 p.m., with storms quickly gaining strength as they move into the instability and moisture axis over central West Virginia. The tornado threat will be highest in the early evening, especially if any discrete cells can remain surface-based and unimpeded by storm mergers. Additionally, the rugged terrain of the Appalachian foothills can distort inflow and create local convergence zones, acting like mini triggers that can intensify updrafts and rotation. So what does this mean for you? If you're in Charleston, Beckley, Clarksburg, or any town within the brown shaded region, have your weather radios on, alerts activated, and shelter plans in place. These setups can escalate very rapidly and may not always come with long lead times, especially if storms form in clusters or along the terrain. So let's break down the timing and probability of severe weather for the Pittsburgh metro area today using this localized forecast timeline. Again, we are under a marginal risk, level 1 of 5, meaning the threat for severe weather is isolated but still possible. The most likely time for any impactful storms in the Pittsburgh region falls between 3:30 p.m. and 10:30 p.m. So let's walk through this timeline. At 3:30, this is the onset window. This is when storms may begin to approach or develop near the region. Notice how the wind, the blue line, and the hail, the green dash line, probabilities begin to rise right around this time. These are signs of elevated convection moving in from the west. Storms that could bring gusty winds and small hail even if they aren't fully rooted at the surface yet. Between 6 p.m. and 8 p.m. is when the peak activity will occur. During this window, we will see the highest probabilities of severe wind and hail, reaching just over 10%. That is a 1 in 10 chance of a storm producing severe criteria within 25 miles of any point in the region. While these are modest numbers, they reflect the low cape, high shear environment that is typical of early spring transitional setups. Storms during this time could produce wind gusts up to 60 miles per hour, marginally severe hail between 3/4 of an inch and 1 inch in diameter, and a very isolated brief tornado, though the red tornado line stays flat, highlighting how low instability may limit tornadic development in this particular zone. After 10:30 p.m. tonight, storm chances drop off significantly as the frontal boundary clears the region and the instability begins to fade. Colder surface temperatures and weakening lift mean that any remaining showers or storms will likely be non-severe. Even though we're not in a moderate or high-risk day, this kind of setup is classic for surprise wind events or marginally severe hail in early season environments. The greatest concern is if we get localized heating or a break in the clouds, allowing surface-based storms to tap into low-level shear, and that's when the isolated tornado risk would materialize. If you live south of I-70, keep an especially close watch as storms entering from Ohio and West Virginia will likely strengthen before weakening later tonight. Now let's focus on Fairmont, West Virginia, which sits in the heart of today's slight risk area, a level 2 out of 5 on the SPC scale. That means organized severe thunderstorms are possible, and some of them could become intense or even damaging. Let's walk through the timeline of concern for today's thunderstorms. Around 4:30 p.m., we can expect the onset of severe weather to begin. This is when the first storms are expected to develop or arrive in the Fairmont area. The environment by this time will feature temperatures rising into the low 70s, dew points approaching the 60-degree Fahrenheit mark, and a weakening cap allowing deep convection to initiate. You can see that the wind, the blue line, and the hail, the green dashed line probabilities start increasing rapidly around this time, signaling the approach of more organized convection. Between 5:30 p.m. and 10 p.m., this is when the peak of the severe weather threat occurs. This is the most critical part of the day, with all 3 severe weather hazards showing highlighted probabilities. The wind, which is the blue line, peaks at over 15%, suggesting the potential for damaging wind gusts of 60 to 70 miles per hour, particularly from bowing segments or fast-moving clusters of storms. The hail, or the green dashed line, also peaks around 15%, indicating a real risk of quarter to ping pong ball size hail, especially with early discrete cells, before the event becomes more linear. And finally, the tornado or the red line, most notably, the tornado risk is present and sustained, hovering around 5% during the entire period, a non-negligible threat, especially given the favorable low-level wind shear across this portion of West Virginia. This makes brief tornadoes or mesovortex spin-ups embedded within a squall line a realistic concern, particularly between 6 p.m. and 9 p.m. tonight. Sunset occurs right in the middle of this peak window, and this can influence storm behavior. As surface instability decreases after dark, storms may begin to weaken, but organized lines can persist well past sunset, especially with the strong upper-level support. At around 11:30 p.m. tonight, this will be the end of the severe weather threat. By this time, most of the storms should have either moved into Virginia or lost access to instability, resulting in weakening convection. The severe risk rapidly diminishes after 11 p.m., and any remaining showers are expected to be non-severe. Fairmont, you are right in the corridor where atmospheric ingredients overlap just enough to support all three severe weather hazards: wind, hail, and even tornadoes. This isn't a high-end outbreak scenario, but the risk is widespread and conditional, and terrain-enhanced flow near Fairmont could locally amplify low-level rotation. Stay weather-aware throughout the late afternoon and evening. Charge your devices, review shelter plans, and have alerts ready. In this type of setup, storms can form quickly and escalate fast. All right, ladies and gentlemen, let's look at the thermodynamic profile for Pittsburgh SKEWT. Where the yellow arrows are spinning there, that highlights the area that I will be talking about. So let's first move into the surface cape at 973 joules per kilogram. This is approaching moderate instability. For April in this region, this is not trivial. This is enough to support robust updrafts, especially when paired with shear. Storms will have buoyant energy for deep vertical growth, supporting lightning, hail, and sustained cores. This is a favorable environment for strong multicells or initial supercell structures if lift is sufficient. Moving on to the convective inhibition. Looks like we have minus 18 joules per kilogram. This is a very weak cap. This is easily breached by heating or low-level convergence. This opens the door to early initiation, which could either help or hinder development depending on how it overlaps with max instability and max shear. Let's take a look at the LCL height, which is 920 meters. The LCL stands for lifted condensation level. It's the height at which an air parcel, if lifted adiabatically or without exchanging heat with its surroundings, cools to its dew point temperature and condensation begins, forming a cloud. The LCL marks the cloud base for cumulus-type clouds in a convective environment. And we're looking at 920 meters again. This is moderate in height, neither too low nor too high. It is low enough to support tornado potential, particularly when combined with low-level shear and sufficient surface moisture. Storms based at this level will have decent inflow and may ingest vorticity efficiently. Next, let's take a look at the LFC height, which is at 1,239 meters. The LFC stands for the level of free convection, and it is the height at which a lifted air parcel becomes warmer than its surrounding environment, and therefore begins to rise freely due to positive buoyancy without needing any additional lifting mechanism. The LFC marks the base of the buoyant or unstable layer of the atmosphere. Above this level, air parcels accelerate upward, forming strong updrafts, which are critical for thunderstorm development, especially for deep convection like supercells. It sits above the LCL, which is where the condensation starts and clouds form. So at 1,239 meters, parcels become buoyant at about 1.2 kilometers. This is fairly low, promoting surface-based convection, not elevated, which is necessary for tornadoes and strong outflows. Now let's take a look at the EL height, which is at around 10.8 kilometers. The EL, or the equilibrium level, is the height at which a rising air parcel, after becoming positively buoyant above the level of free convection, or the LFC, becomes equal in temperature with the surrounding environment again. At the equilibrium level, buoyancy becomes zero and the parcel stops accelerating upward. This marks the top of a thunderstorm's updraft, especially for deep convection. The EL usually corresponds to the anvil top of a cumulonimbus cloud, the flat spreading part of the storm seen at high altitudes. And the difference in height between the LFC and the EL helps determine CAPE, or convective available potential energy, which measures the storm's potential strength. So at 10.8 kilometers, Deep convection is supported. Storm tops can reach well into the upper troposphere, promoting lightning, ice phase processes, and severe thunderstorm development. Updrafts that reach this level are capable of sustained vertical motion and organized storm structure. Taking a look at 3 Cape, which is at 70 joules per kilogram, 3 Cape is the amount of buoyant energy available for rising air parcels specifically within the 0 to 3 kilometer layer above ground level. It associates or isolates the Cape in this shallow layer to assess the potential for strong low-level updrafts, and this is especially important for tornadoes, low-top supercells, and enhanced vertical stretching in the lowest layers. Our value here of 70 is still a bit low for strong tornadic development, but approaching the threshold, which is around 100 joules per kilogram, where low-level stretching becomes sufficient. Combined with decent low-level helicity, this supports a marginal tornado risk. Let's take a look at precipitable water, or PW. Our value is 1.09 inches. Precipitable water is the total amount of water vapor in a column of the atmosphere from the surface to the top of the troposphere, and if all of it were condensed and precipitated as rain. It gives forecasters a quick way to assess atmospheric moisture content. Higher values indicate heavy rainfall potential, enhanced risk of flash flooding, and lower values usually indicate dry air, which can suppress deep convection or lead to evaporative cooling and microbursts. General guidance is less than a half an inch equates to very dry air. Between 3/4 of an inch and an inch and a quarter equates to moderate moisture, supportive of showers and storms, which is where our value lies in. And greater than an inch and a half equates to high moisture content, favorable for very heavy rain. So the interpretation of 1.09 inches, moisture is sufficient for storm development, but not high enough for widespread flash flooding. Values in this range often lead to efficient rainfall cores within strong cells and moderate lightning activity. Now taking a look at the surface temperature and dew point. Surface temperature is at 70 degrees, dew point at 57. The interpretation of this is a 13-degree spread, which equates to a moderately moist boundary layer. This supports surface-based parcels and reduces risk of elevated convection. Dew points in the upper 50s are adequate for sustaining inflow and strengthening updrafts. Moving on to convective temperature, our value here is 73. The interpretation is at 70 degrees, we're just shy of the trigger point. A degree or two of surface heating is likely to initiate convection, especially with any lifting mechanism, which could be a cold front, prefrontal trough, or mesoscale convergence zone. Moving on to storm potential indices, let's start with the K-index. The K-index is a thunderstorm forecasting index used to estimate the potential for convective activity. It's based on temperature and dew point data from 3 layers of the lower atmosphere. Our value here is 30. The interpretation is it is on the lower end of severe thunderstorm support. Usually between 30 and 40 is the threshold. This suggests isolated storms more likely than widespread convection, depending on forcing. This could indicate dry air in the mid-levels, possibly suppressing more widespread vertical motion. Moving on to the TT index, or the total totals index. This is a stability index used to estimate the potential for thunderstorm development and severity. Our value here is 53. This shows solidity in the severe storm threshold range. It also suggests a moderately unstable environment and the potential for hail, wind, and lightning with mature storm cells. Moving on to the surface to 1 kilometer EHI. The EHI stands for the Energy Helicity Index. This combines instability and low-level wind shear into one parameter. It's used to assess the potential for rotating thunderstorms, especially supercells and tornadoes. Our value here is 0.8. This is just below the value of 1.0 threshold, typically associated with tornado-supportive environments. This suggests that if localized helicity increases via boundary interaction or storm scale convergence, tornadoes cannot be rolled out. Moving on to the effective inflow layer storm relative helicity. In meteorology, this is a refined version of the storm relative helicity that takes into account the most unstable part of the atmosphere where storms are actually drawing their inflow, not just a fixed surface-based layer. Our value is 166 meters squared per second squared. This value is supportive of low-level mesocyclones. Being that this value is greater than 100 meters squared per second squared in the surface to 1 kilometer layer is a red flag for potential tornadoes, especially if directional shear, veering with height, and instability coincide. Moving on to the critical angle, value of 52 degrees. This is excellent for ingesting streamwise vorticity into an updraft. Tornado supportive critical angles are generally above 45 degrees. This one is very favorable. If storms form with discrete or semi-discrete character, this environment supports rotating updrafts. Taking a look at BRN shear, our value is 78 meters squared per second squared. This falls squarely into the supercell supportive zone between 45 and 100 meters squared per second squared. This shear and cape balance suggests that storms will organize well with good tilting and separation of updrafts and downdrafts. This could support right-moving supercells or long-lived multicellular clusters with rotating updrafts. Next, let's take a look at supercell composite. Our value is 3.2. Values above 1 are often correlated with supercellular environments. At 3.2, this suggests enhanced confidence in supercell formation, especially with modest instability and good shear. This environment could support rotating storms with large hail and damaging winds, and perhaps a brief tornado or two, especially if a boundary enhances low-level shear locally. Right below that, let's look at the STP SIN adjusted. Our value is 0.7. The significant tornado parameter in the range of 0.5 to 1.0 range is a marginal risk, but noteworthy. Combined with favorable helicity and critical angle, this suggests that if a discrete storm forms, a brief or weak tornado could occur. If this number nudges closer to 1 or above in the future updates or mesoscale discussions, we have to watch that very closely. Next, let's take a look at the D-CAPE. Our value is 442 joules per kilogram. This is borderline. It's not high enough for widespread downbursts, but enough for isolated damaging wind gusts. Coupled with dry air below cloud bases, this could produce localized strong outflows from collapsing or rain-cold cores. Looking at the SKEWT log-P diagram as a whole, the environment across western Pennsylvania is showing signs of moderate instability, sufficient moisture, and enhanced wind shear, particularly in the lowest kilometer. If surface temperatures rise just a few more degrees, expect storm initiation during the afternoon to early evening. Storms that form may become organized and rotating, supported by favorable wind profiles and deep layer shear. The primary concerns are damaging winds, hail, and possibly an isolated tornado, especially with any boundary interactions or discrete storm cells. Stay alert and monitor radar updates as storms develop. All right, moving into the Fairmont SKEWT. Let's take a look at the surface cape at 1,099 joules per kilogram. Again, this is the convective available potential energy. This equates to the updraft strength potential. The interpretation of 1,099 joules per kilogram is moderate instability, especially for early to mid-spring. Updrafts with this level of cape can sustain deep convection, drive strong vertical velocity, and support large hail if mid-level lapse rates are steep enough. Storms in this environment can quickly organize and become severe, especially if supported by favorable shear, which we do see here. Taking a look at the SIN, or convective inhibition, which is the energy cap that must be overcome at minus 23 joules per kilogram. This very weak cap means storms will initiate easily as surface temperatures reach the convective temperature, which is approximately 75 degrees. We have to watch for rapid development near the afternoon peak heating window, and no significant inhibition means storms can erupt quickly. Moving on to the LCL height. Again, this is the lifting condensation level. This is the approximate cloud base at 1,016 meters. This is a moderate cloud base, low enough to help stretch low-level vorticity in supercells if other ingredients like storm relative helicity and energy helicity index are present. It's not too elevated, so the tornado risk is not limited by the LCL height in this case. Moving on to the LFC height, or the level of free convection. This is the height where parcels rise freely. At 1,350 meters, this confirms surface-based convection, not elevated. It also ensures storms are able to efficiently ingest boundary layer helicity, which is a key factor for rotation. Moving on to the EL height, or the equilibrium level. This is the storm top potential. At around 11 kilometers, this indicates very deep convection supported. This means strong sustained updrafts, lots of lightning, and hail production potential. Updrafts that reach this level will likely penetrate well into the upper troposphere. Moving on to 3 Cape. This is the cape in the lowest 3 kilometers. This supports tornadogenesis via stretching. At 49 joules per kilogram, this is still modest but higher than previous setups. When combined with good low-level helicity and a supportive critical angle, this can still support brief tornadoes, especially in strong updrafts within a supercell. Moving on to PW, or precipitable water. This is the column moisture availability. Looking at 1.24 inches, this is above average for April, indicating a moist environment. Expect heavier downpours, efficient rainfall processes, and saturated updraft bases, which further supports storm longevity and lightning. Combined with high CAPE, this supports moisture-rich supercells and possible flash flooding in training convection. Taking a look at the surface temperature and dew point, surface temperature of 72 degrees and a dew point of 58. A 14-degree dew point depression suggests moderate surface moisture. This is high enough to support surface-based parcels and sufficiently moist boundary layer inflow into storms. This also helps enhance buoyancy and maintain strong storm strength once initiated. Moving on to convective temperature. Looking at 75 degrees Fahrenheit, current surface temperature around 72 degrees, which is just 3 degrees shy of initiation. Only a bit more heating or localized convergence is needed for storms to erupt. Taking a look at storm and severe indices, let's take a look at the K index first. Value of 36. This is good for supporting general thunderstorm coverage. Moderate values like this help confirm the environment is right for scattered to numerous thunderstorms, especially in combination with synoptic lift. And then looking at the TT index, or the total totals index, a value of 54. This is in the range supportive of severe thunderstorm development, indicates decent lapse rates contributing to hail and strong downdraft formation. Moving on to the tornado and rotation parameters, let's take a look at the surface to 1 kilometer EHI, or energy helicity index. Our value is 0.9. This is just under the 1.0 threshold, but strong enough to flag rotating updraft potential. With any enhancement from boundaries, this could easily nudge higher, supporting brief tornado development. Taking a look at effective inflow layer storm relative helicity, a value of 141 meters squared per second squared. This is a solid shear value for early season convection. When the value goes above 100 meters squared per second squared, supercell organization becomes more likely and brief tornadoes or mesocyclones can develop. Effective inflow SRH, or storm relative helicity, over 100 to 150 meters squared per second squared is adequate for rotation if storms are surface-based, and this profile supports that. Moving on to the critical angle, our value here is 61. This is an excellent value, high enough for optimal ingestion of streamwise vorticity into the updraft. This strongly supports mesocyclogenesis, especially if storms are discrete or semi-discrete. Taking a look at the significant tornado parameter, SIN adjusted, our value is 0.7. This is just shy of 1.0, which is considered the significant tornado threshold. In this case, the overall environment is primed, and any mesoscale boundary or differential heating, outflow, things like that could raise this locally. Tornado potential is conditional, but very much present. Taking a look at BRN shear, 93 meters squared per second squared. This is right in the sweet spot for supercells, which ranges from 45 to 100 meters squared per second squared. This implies that storms will have excellent updraft and downdraft separation, promoting longer lasting rotating storms. Next, turn our attention to supercell composite, value of 3.1. This is very supportive of supercell structures, suggests a clear window for at least isolated rotating storms. Coupled with surface-based instability and solid shear, this supports supercell thunderstorm development, possibly with large hail, damaging winds, and a brief tornado. Lastly, we'll look at the D-CAPE at 655 joules per kilogram. This is a high-end value, strong potential for downbursts and damaging straight-line winds. This is especially dangerous if storms collapse or become outflow dominant. Gusts of 60 to 70 miles per hour, particularly where drier subcloud air enhances evaporative cooling. We're going to have to watch that carefully. Possibly up to 70 mile per hour wind gusts, folks. Taking a look at the SKEWT diagram for Fairmont, West Virginia as a whole, the thermodynamics show strong CAPE, moist boundary layer, deep storm tops. The kinematics show supercell supportive shear, solid helicity, and near critical significant tornado parameter. The initiation potential is very likely by mid-afternoon. The storm mode will be discrete cells possible early, and then clusters including supercells after that. Primary hazards include damaging wind gusts, frequent lightning and heavy rain, brief tornadoes, and large hail. We're going to have to watch for outflow boundaries and temperatures rising above 75 degrees, as this will rapidly break the cap. Storms forming west and moving into this environment could mature into rotating cells. Storms are likely to develop across Fairmont and surrounding areas this afternoon. Conditions are supportive of supercell thunderstorms with the potential of damaging winds, hail, and even a brief tornado. Storms may initiate quickly with minimal warming. Stay weather aware, folks. Have multiple ways to receive alerts and be prepared to take shelter if warnings are issued. All right, ladies and gentlemen, that wraps up my in-depth breakdown of the severe weather potential across the region today. As always, I'll continue monitoring model guidance, real-time radar, and mesoscale trends, and will provide nowcasts if conditions escalate. Check me out on Facebook. I'll leave the link in the description there. If you found this information helpful, please hit the like button, subscribe to the channel, and leave a comment below, whether you're a weather enthusiast, a student, or just trying to stay safe today. And most importantly, share this video with anyone who needs to be weather aware today. Your family, your friends, your community. Stay safe, stay sharp, and stay ahead of the storm. I'm Zach, and I'll see you in the next update.